Okay, so good afternoon. So thank you for still being here. Yeah. So my name is Jianjia Yu, and I'm currently an assistant professor of chemical engineering, and I'm also a research scientist at the Petroleum Recovery Research Center. So at PWRC, so we have been working on water treatment for more than 20 years. Yeah. So everybody knows. So actually, we sit on the desert. Yeah. So we don't have a lot of access, to the fresh water. Yeah. So there's some data here, just for your reference. So right now, 87% of the public water supply actually they come from the groundwater. Yeah. And right now, yeah, if you look at the aquifer, actually underneath of us, this aquifer, they are just declining. Yeah. So we need to find a new water resource. And at another aspect, so we produce a lot of produced water. Yeah. So when I talk about the produced water, so that is the wastewater associated with the production of oil and gas. So typically when we produce 1 barrel of crude oil, so there are 7 barrels to 10 barrels of water with the oil. Yeah. So the treatment of the produced water actually is a big challenge. Yeah. So you see, it's interesting. We don't have fresh water, but at the same time, we produce all the wastewater. Yeah. So the treatment of this wastewater is very expensive. Yeah. So for example, if you look at the Permian Basin and the San Juan Basin in New Mexico, so they have to spend about, as high as $4.40 just to get rid of each single barrel of the produced water. Yeah. So why we do not use the produced water as a resource? The reason is because, the produced water desalination or the produced water reuse actually is very challenging. Yeah. So number one is, in the produced water, there are a lot of contaminants. Yeah. So in general, we use the salinity or the total dissolved solid to describe, so how much contaminant, in the wastewater. So if you look at here, so the produced water contains, more than 200,000 milligram per liter. Okay, if we look at the ocean water, the sea water is 25,000. So this is 6 times higher compared to the ocean water. And there is also a lot of organic, just like the floating oil in that produced water. Yeah. So this kind of contaminant, makes the produced water very difficult to be challenging. If you look at the market, actually there are no available technology, to do the produced water desalination. So for me, actually at PWRC, so our major research interest, is to develop the affordable, portable, and scalable. Yeah. So we are trying to make the desalination unit as small as possible, so we can do the desalination at each different produced water production site. Yeah. And we are trying to convert, the produced water from a waste to a sustainable water resource. So actually, we are recovering the high purity clean water as a water resource. And from the concentrated produced water, we noticed there are a lot of critical minerals and energy materials, such as ammonium, like that. So we are trying to recover the water and the critical minerals and ammonium at the same time. Yeah. So most of my research is based on the hollow fiber membrane. Yeah. So actually, the reason you use hollow fiber membrane is like this. Yeah. So actually, it's very portable and it's very scalable. Yeah. And so we can reach a very high water treatment capacity by using a very small footprint. Yeah. And right now, so actually we're working on a couple of different projects. So we are doing the water extraction, and we do the critical mineral reaction, and we also do the gas separation. So because I just have 15 minutes, so today I just want to focus on using a membrane destination, to treat the high salinity produced water. So this image shows what is the membrane destination. So actually, so here is the membrane. So on one side of the membrane, so we have a high salinity wastewater. And what we do is we heat this kind of produced water to a certain temperature, and on the other side, so we can extract the high purity clean water from the hot side. I keep saying high purity. The reason is because this process actually is thermal driven. So basically just the vapor passes through the membrane. Yeah. So when we look at the quality of this membrane, so this is super clean water. Yeah. So we can use this water for a lot of beneficial purpose, such as in the semiconductor industry. Yeah. Another advantage is when we use this process, we can use the renewable and low grade heat as the heat resource. So right now, there are a lot of interest, in the geothermal. Yeah. So we are currently working on a DOE project. We are trying to use the geothermal, to drive the desalination. And we put the water out from the geothermal wastewater, and at the same time, So we can increase the concentration of critical minerals, and that will help, to the recovery of the critical mineral. So this process is not new, yeah. But right now, this process has not been commercialized. The biggest challenge is right now, so there's no membrane, there's no commercially available membrane to achieve, this process. So let's take a look at, this membrane here. So when we talk about, the desalination, especially the vapor transfer from the hot side to the cold side. So actually the vapor transfer and also the heat transfer. So when we talk about the heat transfer, so we have two different kinds of heat. So one is the heat to generate the vapor and to collect the vapor as a clean water. Another heat is the conductor heat. So this is the heat get lost during the process. So in this process, we are trying to maximize the use of the latent heat, and we want to minimize, this heat. So when we look at these equations, so actually the thickness, plays an important role. So typically, if you increase the thickness, so you can reduce, the waste of the heat. But also, if you increase the thickness, so the mass transfer actually will be reduced at the same time. So what I do is actually, so we designed actually a new membrane. So actually, so we, so this one is a, it's a patent, it's on, it's still on pending. So what we do is we make the membrane as a genus. When we talk about genus, so that means, so this membrane has two different components. So we have a hydrophilic component, and actually we have a super hydrophobic component. So when we use this membrane to do the desalination, as you can see, so we can keep the thickness of the membrane to resist the heat loss, and we can also increase the vapor flux, during the desalination, yeah. And this image, shows how we fabricate the membrane, yeah. So basically, this process is very scalable, yeah. So if everybody has an interest to see how we fabricate this membrane, so you can go to PwC and I can show you, yeah. So here's the membrane, and here's how it looks like, yeah. So, so the diameter actually just 1 millimeter, yeah. So that is very small, So here is the micro morphology of the membrane. As you can see, so there are two different layers. So that's why we call this one is a genus membrane, yeah. If you look at it closely, so it's very porous. So by this kind of structure, so we can make sure, so there is a high vapor transfer rate during the desalination. If you look at the outer surface and the inner surface, so the water contact angle or the wettability is also very different. The inner layer is very hydrophilic and outer layer is very hydrophobic. So we use this membrane to do the desalination, And when we compare, so when we compare our membrane, so with the commercially available membrane, so as you can see, so we can increase the water flux and we can increase the energy efficiency at the same time, yeah. And this green line, shows the flux of the most commercially reverse osmosis flux, as you can see. So when we deal with the water with different salinity, so we show a much, much higher water flux. So that indicates a much higher productivity. So we also run long-term operation. We want to see, so how stable this membrane is, for long-term operation. So we run it continuously for 200 hours. So that's 7 days. As you can see, the flux is very stable. Actually, here we use the seawater. And if you look at the conductivity, it's below 5. Just for your reference, the drinking water, is this level. Even when you use the reverse osmosis, so the conductivity is about 10 to 20. So that's why I say this water is ultra pure water. So that is what semiconductor industry need, yeah. And we also test the stability when we use the oil field produced water. As you can see, here is the original produced water. It has organic and it's very dirty, yeah. So we do a simple pre-treatment by using a 50 micrometer pre-filter, and we get the clean water. So when we look at the flux, it's also very stable. And when we look at the salt rejection, so it's interesting. Actually, so water we recovered actually become cleaner and cleaner, with the operating time, because we just recover the vapor as a product, yeah. So we also do a economic analysis, and here's the result, yeah. So if we can use the renewable energy, yeah, or if we can use the geothermal heat, so we can achieve 10 cents for each barrel of the produced water treatment. And even if we just use the electricity or use steam, so the cost is about 87 cents for each barrel. Yeah, so right now, most of the industry, if they get rid of each barrel of produced water, so they have to spend about 67 to $1, yeah. So this is comparable, with the disposal cost. So based on the membrane, so actually we already learned, the scaling is very hard. The scaling is challenging, yeah. So in the past in the past about 10 years, so we did a lot of upscaling work. So this one shows a pilot testing. So we finished it in 2014 to 2016. And this project is funded by the Department of Energy. So we use this unit so we can produce 5,000 gallons of the clean water actually from the produced water. And another example is we also use this water to recover the phosphorus and ammonium, from the dairy industry wastewater. So we do this kind of pilot testing in Clovis, New Mexico, and we can achieve 99.7% of the removal of the nitrogen and phosphorus. And most recently, so we also work very closely, with a local manufacturing company. So that is the process and equipment service company. So we work with PESCO actually. So we have built this kind of modular unit. If you look at this unit, okay, so this one can produce 5,000 gallons of clean water per day. This one is 500 gallons per day. So what we do is at New Mexico Tech, so we fabricate the membrane at PWRC and we build up this kind of membrane module. So this is so scalable. So depending on how much water you are trying to produce or you are trying to treat, so we can easily to scale up, this unit to achieve different kind of capacity. So our research actually is supported, by different federal agency. So right now we have one project actually supported by the Bureau of Reclamation, and we are trying to recover the lithium, from the high salinity brine, and we are trying to produce, ultra pure water. And we also have an active project funded by the Department of Energy through the energy efficiency and renewable energy. So for this project, we are trying to increase the concentration of lithium by using the geothermal energy. And at the same time, we recover high clean water. And we also have 2 projects funded by the DOE through the fossil energy and carbon management. So that is to characterize, the resource of critical minerals, in the whole New Mexico. So we are trying to build a pilot scale unit. So do the water recovery and also the lithium extraction at the same time. So this work actually is a collaborative effort, with the Sandia Lab, New Mexico State University, and the University of Wyoming. And also, so our project actually is funded by the state and by the, by the REPC and some private company. So that's all for me. Thank you.